Hey everyone, this is week 6, chapter 6. We're going to talk about shape. This is the last chapter for exam 2, and really just piggybacks off of our last chapter where we talk about Lewis dot structures, and then this is going to show you the rest of the story where you realize that even though we draw Lewis dot structures two-dimensionally on paper, they're really three-dimensional, just like our bodies are three-dimensional and not as flat as a sheet of paper. So as we look at examples, we need to realize that molecular shape is important. When you think of drug molecules in the body, the shape of the molecule is what helps it fit in the right spot, and it helps prevent it from fitting into other locations to give side effects and so forth. So shape and polarity are really what make all medicine work, because it has to have the right shape, the right polarity to both fit and to attract to that active site and relieve those symptoms. So we'll talk about polarity last, probably in a separate video, and that'll just remind us of our definitions about polarity from our last chapter, but it'll also help us understand polarity and the scope of shape along with it. So again, one of the problems with Lewis dot structures is they're flat. They're on a sheet of paper, they're on a whiteboard, and we need to realize that the world has shape, and the molecules and the atoms that make up that shape also have shape. And that's where we're going to kind of break it down into their most simplest forms in this chapter. And then if you take Gen Chem, you'll learn about more advanced shapes and so forth. So one of the major theories of this chapter is called Vesper Theory. Vesper Theory is valence shell electron pair repulsion theory, and it sounds like a mouthful. It shouldn't be too scary to think that valence shell electron pairs, so outer electron pairs, repel each other. Electrons are negative, and if they get too close to other atoms that have negative electrons on their outside, they're going to push back. So our job in this chapter is to realize that as electrons push on other electrons from other atoms, how far can they push before they get pushed back on atoms from the opposite side of that particular atom. So as we look at something like methane, we have to realize that, sure, we have carbon from group 14, Roman numeral 4, and what's most important about that one is that you would expect 4 bonds, because if it has 4 electrons, it's going to need to share 4 more electrons to get the magic number of 8, like those noble gases, in this case, like neon. So what tends to happen in this situation is we draw this flat structure, and the disadvantage of this flat structure that looks kind of like a cross, looks like kind of like a 4-way stop, is the bond angle over here is going to be pretty close to 90 degrees. At least on paper, that's what it's going to look like. And then this distance here is going to be more like 180 degrees. So the reason that's not good is because these atoms are too close and these atoms are too far away. Is there a happy medium where we can allow those atoms to get in a distance that's, in a bond angle that's somewhere in between 180 and 190. And it turns out that's going to be what we call tetrahedral, with that's 109.5 degree. So what happens here is carbon has 2 in the plane, and if it has 2 in the plane, those are relatively flat to one another. But then we will draw this wedge that represents a forward hydrogen that's projecting forward through the screen of the computer that you're watching this on, and then this dashed or dotted line is going to go backwards. Hopefully this will help allow you to better see that this is kind of like a pyramid in a way. As you look at this face here compared to this face here compared to that face back there, it's a lot like what we would call a pyramid, but pyramids are a little bit squattier underneath. The reason we call this a tetrahedron is because it has 4 faces. So here's 1, here's 2, the back side is 3, the underneath side is 4. There's 4 faces that are perfectly equal. And that's because the angle between the hydrogens in a tetrahedron are 109.5. And this is what's unique about the carbon atom itself. It forms this kind of pyramid-like structure that we call a tetrahedron. So in chemistry, we call it a tetrahedral shape. So what we just demonstrated there is atoms have directions from their center. This directions is what the textbook calls steric number. Steric number is basically this compass-like orientation of the atoms around the center atom. And you could think of it a lot of different ways. I like directions more than steric number just because it's more relatable. But really, the reality of this is we have 4 different steric numbers. The one that we just saw with methane is an obvious steric number of 4 because it had 4 hydrogen atoms attached to it. And that tetrahedron-like shape, this tetrahedral that we call it, it is our major classification for having 4 directions or 4 steric numbers for different directions from that center atom altogether. Just make sure that when you're looking at steric numbers, you're including the number of atoms and you're including the number of lone pairs. Turns out with Vesper theory, valence shell electron pairs that aren't participating in bonding actually take up more space than those that are in the bonding. Because you can imagine that if you're stuck in a bond, you're really stuck most of the time between those 2 atoms, and that's a very confined space. A lone pair is not being shared with anyone, so it has freedom to roam about that p orbital in most cases. So in that dumbbell kind of shape, and because it has a large real estate of area that it can move around in, it's also going to have a lot of repulsion. So as we look at another example with formaldehyde, notice we have a carbon, 2 hydrogens, and oxygen. Very important to know that hydrogens can never be center atoms because they only share once. This would be very similar to what we would see with halogens. Halogens are only going to share once because they already have 7. They only need 1 more to share to get 8. So putting them in the middle would be starting off on the wrong foot, so to speak, and making that answer harder to find. So keep atoms like carbon and like oxygen in the center. When we do that on this example here, what's important to know is that you do have 2 options, carbon or oxygen, being in the center, but realize that carbon has more bonding possibilities than oxygen, so it's the more likely center. The reason we know that is because carbon's in group 14. It's going to want to share up to 4 times. Oxygen's in group 16. It already has 6, only needs 8, so it only needs to share up to 2 times. So keep it on the outside makes more sense in this situation. One thing I like to do also is remember that atoms like to be symmetrical. So if atoms and their molecules that they make are symmetrical, let's put carbon in the middle. Let's put these hydrogens off to the side. And then oxygen up top or down low, doesn't really matter. The next thing we're going to do is look at the periodic table, much like we could have done with carbon in the last slide that was already kind of done for us. We need to go and look at our valence electrons. The easiest way to find that is the ones place of their 1 through 18, or just the Roman numerals. Either way works. You're going to see that carbon is in group 4. So it has 4 valence electrons. Hydrogen's in group 1. And then oxygen's in group 6. So just like last chapter, remember, we're trying to aim those single dots at each other so they have a better chance of connecting without drawing through the symbol and making it look kind of weird. So here we're going to make hydrogens happy first. That's going to be the easiest situation. I'm going to take this one underneath just to make it a little bit easier to see what's going to happen up top, and that's that oxygen and carbon have to share twice through what we call a double bond, and that's what we've seen in our previous chapter as well. So if you look at the bare bones of this particular structure, you're going to notice that different from methane. Methane a moment ago, if you remember, had carbon in the middle with 4 hydrogens around, and that looked kind of like a cross. That cross-like orientation is what we would call that steric number of 4 because we have an up, a down, a right, and a left. Notice in this situation with formaldehyde, what we really have is an up to that oxygen. We have kind of a left and kind of a right. This is what we call a steric number of 3 because it only has really 3 directions from that center atom, not 4. So when we draw the electron dot diagram, we do end up with a double bond and 2 single bonds. When we look at the steric number, we see that there's really no bottom, right? There's nothing going down from carbon. There's kind of a west and an east, and then a north, no south, so to speak. And then when we predict the angle here, you'd have to think that if this is a circle, we're really just cutting that circle into 3 evenly, spaced pieces. If a circle is 360 degrees, when you do a donut in a parking lot, that would be the case. Here we just look at one of those pieces a third of that would be 120. So the angle between these atoms up here is going to be 120. So as we look at these examples, just remember that we have three choices. A steric number of 4 is when we have 4 groups, whether they're bonds or lone pairs doesn't matter. We'll see some examples of those coming up. But when you have a double bond, you can almost guarantee that you're going to lose a direction because 2 of those bonds are going to the same atom. And that's what's happening here with formaldehyde. So because of our double bond, we lost a direction. Now both of those bonds are going in the same direction, so that gives us this steric number of 3, which is our new category. And then again, this 120-degree angle is perfectly flat, and it shapes what looks like a triangle. So if you think about these atoms up here like we did before, this is like a triangle, but now it's flat. And that's where they get that idea of triangle flat, or in our case, trigonal planar. Makes it sound a little more scientific, but basically the same idea. Let's try another one. So here we have hydrogen cyanide, and the only way to make this one symmetrical is really just to draw it exactly as it appears on paper, and that's to draw H to C to N. And then we go to the periodic table to look at valence electrons. We're going to see that hydrogen again is in family 1. Carbon's in family 4, so give it 4. It's in group 14, use the ones place. If you don't like the Roman numeral, nitrogen group 15 or Roman numeral 5. Next, what we're going to do is connect the single dots only. So if we connect the single dots here, that makes hydrogen happy and hurry. Carbon likes to share 4 times. It's already sharing once, so let's let it share again, again, and again. And notice now we get this triple bond. What's most important about this feature is this allows us to realize that we're only going kind of left and right. That is a steric number of 2. So a steric number of 2 tells us there's only a left and a right, and the difference between hydrogen and nitrogen in this shape is a straight line. Straight line has a 180-degree angle. And that's what we're after in this particular idea. So again, steric number of 2, here we have a shape of a straight line, so we just call that linear. And this is probably one of the easiest shapes to think about. And this will happen anytime you have triple bonds. It'll happen anytime you have 2 atoms, because the only difference between 2 atoms is going to be a straight line, whether that's a single, double, or triple bond. It's still going to be 2, 3, or even 1 straight line between 2 atoms. Or then in some rare cases, you might see 2 double bonds making linear. But definitely anytime you have multiple bonds, you're in that steric number of 3 or 2, but triple bonds are always going to be in that steric number of 2 kind of category. So here's kind of a summary of the different steric numbers. So in a separate video, we're going to come back and talk about exceptions to these steric numbers. But really what we have again is this idea of 2 versus 3 versus 4. These are what I would call the categories of shape in Introchem. Remember that if you have a steric number of 2, think triple bonds. So triple bonds are the most common way to recognize a steric number of 2. They do show you here that carbon dioxide is an example where you can have 2 double bonds. That can also work. You can also think of having just 2 atoms where you're talking like hydrogen attached to hydrogen. That's obviously a single bond and only between 2 atoms, which is a straight line. So anytime you have 2 atoms, triple bonds, or 2 double bonds, you'd expect a steric number of 2. With a steric number of 3, think about having double bonds. Double bonds are going to be almost always in this directional 3 steric number kind of concept, because you're always going to have 2 bonds going in that same kind of direction, which a lot of times is up systematically, but it could be down just as well depending on how you draw it. They do make that flat triangle kind of shape. They do cut a circle 3 ways to get their bond angle, but double bond is a great way to recognize this trigonal planar shape as a category of shape. The only time shape really changes is with lone pairs, and we'll see that in a separate video. Just remember, though, there are examples like CO2 where you have 2 double bonds, and that straightens you out completely, and that's going to get you back to that category of 2. And then when you're dealing with this steric number of 4, think single bonds. If you have only single bonds, and as long as you're not 2 atoms where you're going to be linear, that's a little bit more obvious. But anytime you have, 4 atoms, 3 atoms, 1 lone pair, 2 atoms, 2 lone pairs, and this would be the case for most carbon, nitrogen, and oxygen families, they're all going to be in this tetrahedral category, although we're going to show in a separate video that there are exceptions to when you add lone pairs. Vesper theory adopts a new, relatively similar shape in that kind of way as well. So here's our shape categories, and then we'll come back and show you better examples of shapes when we introduce lone pairs.